Another quantity that we need to talk about when we're talking about electricity and circuits is resistivity, and then kind of the circuit quantity that goes along with it is resistance. And so voltage is going to drive a current, and the amount of current depends on that voltage and the material that it's flowing through, whatever it's made out of, and its geometry. And you can think of it kind of like a pipe, a big empty pipe. You're going to get a lot of water flowing through it. A little tiny pipe or a clogged pipe, you're not going to get so much water. And it's very, very similar if you're thinking about resistance and resistivity in those terms. Now, conductivity just tells you how well the electricity is going to flow. It's conduction, and it can be heat or electricity. And it's the reciprocal of resistivity. And so they are reciprocals of each other. So resistivity, it's the rho. It's a measure of how much material resists charge flow. It's a table, and you won't have to memorize it. I'll give those to you if you need them. The higher the resistance, the more insulating it is, the higher the resistivity is going to be. And inversely, the more conductive it is, the more metallic even, the greater the conductivity is going to be. So they are reciprocals of each other. So as temperature changes, resistivity changes, and I think you've seen that in a lab. Your resistance changed, and the relationship is right there. It's the resistance is multiplied by a factor that includes something called the temperature coefficient. And once again, that's in a table. It depends on the material. A positive temperature coefficient is going to increase the resistivity, and a negative coefficient is going to decrease the resistivity. So you can't always say that as it heats up, the resistance is going to go up in the resistor. It's going to depend on what it's made out of. And the other piece to this is the geometry. So we talked a little bit about the pipe. A big, wide pipe is going to carry a lot of water. And the other piece is the longer the pipe is, the more resistive it is. So the longer the wire, the more resistive, and then the smaller the diameter, the more resistive it is. You'll also see that the symbol for resistor is a little zigzag. And you'll see that in the symbols when we start talking about circuits in the next chapter. All right, so on the molecular level, the resistivity of a material times the current density is going to be related to the electric field. And if you remember, the magnitude of the electric field in a wire is, or a segment of wire, is just the voltage divided by the length of that wire. So we're going to end up with the voltage divided by the length is rho, resistivity, and then the current density is the current divided by the area. If we do some rearranging on this, we have voltage is rho times the length over the area times the current. And that rho L over A is just the resistance in the wire times the current, or we end up with Ohm's law, which is voltage is current times the resistance. And this would, for ohmic resistors. And so that tells you that the voltage is proportional to the current. Ohm's law. Resistance is measured in ohms. The symbol in the equation is a capital R. And we talk about it as being ohmic if Ohm's law holds, which would be the voltage is proportional to the current. There are times when things aren't ohmic and you end up working with curves and best fit lines, but for the most part, we're going to deal with the nice, straightforward ohmic type circuits. Okay, so I have a little example of an Ohm's law problem, and then one that deals with the change in resistance with temperature. So we start off with a resistor has a temperature coefficient, some material, of 4 times 10 to the minus 4 per degree C. And it's going to carry a current of 2 milliamps when it is attached to a 12-volt source. So this is a nice, straightforward Ohm's law problem. 12 volts is the voltage, and then 2 milliamps. Don't forget you have to work with amps and volts and ohms when you're doing Ohm's law. And when you do the math, you end up with 6,000 ohms for your resistance, and that's at room temperature. Now, as it keeps going, resistor heats up, and depending on what the coefficient is, it may actually increase or decrease the resistance. And so you'll see some of the coefficients with negative numbers, and so that means it's actually going to decrease the resistance. So in this case, we have a positive number for a coefficient, so the resistance is going to go up. And the equation for this is just a rewrite of the resistivity change in temperature. If you go through the algebra, everything is rho L over A, so they all fall out. So you have your initial resistance, 6,000 ohms, is 1 plus the coefficient times the change in temperature. And so the change in temperature is going to be 26 degrees C if we assume room temperature is 24 and subtract it from the 50 degrees C in the problem. And when you work out all the math, you don't end up with very much of a change. So that considerable change in temperature, making the resistor a little bit hot to touch, does not really change the resistance of this material considerably. When we're talking about electricity, you got to talk about power. And so, you got your electrical power, you pay for it, kilowatt hours. And so power is the rate of change of work with energy or time. And so it's measured in watts, and it is the power's work over time, if you remember from mechanics. It is also the change in the amount of charge times the voltage over time, or current times voltage. Also, it is the voltage squared over the resistance. So there's a lot of different equations for this, and it's all interwoven with Ohm's law. Choose the one that works best with the information that you have. So my example problem for power is going to be one that kind of combines mechanics and electricity. We've got a motor, an electric motor that's lifting a 500 kilogram crate 3 meters upwards, and it does that in 30 seconds. And it's pulling 10 amps, and it's a 110 volt motor. We're going to assume it's DC. We're not going to deal with alternating current right now. And I want to know how much power is used by the motor. And so we have a lot of power equations to choose from, and they're all just rewrites of Ohm's law and the power equation. So the one that's convenient is current times voltage. And so we have that 10 amps times 110 volts. So that's 1,100 watts is the power. And if we want to know how much work is done lifting the crate, we go back to power is work over time. And that work is equal to force times distance over time. So we end up with that 500 kilograms for the mass of the crate times the acceleration due to gravity times the distance that we lifted it divided by the time it took to lift it. And so that ends up being 490 watts. So you can see that the work done was much less than the electrical work provided to the motor. So we're going to assume that that loss is due to some kind of a resistance in the motor, and we're going to find out how much that resistance is. And so we take the difference in the powers and plug it into one of the power equations for electricity. And we end up with a resistance of 6.1 ohms in our motor. And then finally, we have the set of equations for the resistance portion of this chapter. And they're a little bit repetitive, but I think they're all fairly straightforward. Good luck. Bye-bye.